Hello, Ms. Nguyen. This is Atid. This is my video for question 1. What is a continuous function? Different types of discontinuities. So what is a continuous function? So it's something that is consistent. It keeps going. It doesn't stop. There are no breaks in the function itself. There's no asymptotes, holes, jumps, meaning you don't have to jump from one point to get to another. It's just like a visual way to identify if your function's continuous or not is, I'll use my finger. Pretend this is my pen. I could draw this in one stroke. I don't need to lift up my pencil to get from here to here, or I can just go in one go. Now obviously you can't write this on a test. We want to prove it. So there's two conditions. So number one, you're gonna have to have your two-sided limit. So the limit, so let's have a represent a number. X approaching a from the left side, so the limit of that has to be equal to the limit of x approaching that number from the right side. So first you have to have your two-side limit existing. So after you have that, that limit has to be equivalent to when you sub that said number into your function. So for example, let's say a. Let's say a is 2. So let's just, for example, say limit of f of x approaching 2 is like 3. Now if I sub in 2 into my equation and I get 3, then my function is continuous. So an example right here. So I chose x, so this is my equation, my sample equation. This is x approaching 2. So x is approaching 2 from the left side. Y goes to 51. X is approaching 2 from the right side. Y is approaching 51. Now when 2 is subbed into the equation, I also get 51. So because the limit of f of x when approaching 2 is equal from the left side is equal to the limit of f of x from x approaching 2 from the right side is also equal to f at a. So when the number is plugged in, this function is continuous. So in general, you can say that if the limit of f of x approaching a from the left side is equal to the limit of x approaching a from the right side is also equal to f at a, your function is continuous. We'll be moving on to a type of discontinuity. So we'll be talking about removable discontinuity. Well, obviously visually, if you're going along this function right here, you'll notice that there's a hole here. So basically, a removable discontinuity is just a discontinuity at like just this one point. This point it doesn't exist. But sometimes you'll find situations where there might be like a point down here. Ignore there's a bad drawing, but you might see that everything is nice. It's going, and then boom, point's right here, and then it just goes back and continues going. Or sometimes this won't even be here. It'll just be like that. So the algebraic way to prove this is limit. So the two-sided limit exists. So that exists. So when you're approaching a number from the left side, so when x is approaching a number from the left side and it's approaching it from the right side, that will be equal. But the problem here is that your two-sided limit will not equal when you plug that number into the equation. So for example, if x was approaching 2 and the limit of x is approaching 2 is, say it's 6, and I plug in 2 into the function equation and I get like 12. So because they're not equal, this function is not continuous. Next discontinuity we're moving on to is infinite discontinuity, so also known as asymptotic discontinuity. So this is a discontinuity in the form of an asymptote. So you'll notice that in this example graph I have here, there's an asymptote at 1. And you'll notice obviously that If you know the pencil test, my pencil, as you're going along it, you know, you'll never be able to get to the top, because you know this asymptote just keeps going. It just keeps going. Your function will never ever be able to hit this number. So as you're going from the left side, you know, you're just going higher and higher and higher and you never reach it. And then to draw this, you obviously have to lift your pencil and keep going and going and going, but you never hit this. So to prove this, you know, you want to do the limits, and what you'll notice for an asymptote is that so in this case it's 1, so when x is approaching 1, so the asymptote from the left side, y is going towards infinity. When x is approaching the asymptote, so 1, from the right side, y is still going to infinity. And obviously this is just for this equation. Sometimes 1 will be going towards negative infinity, 1 will be going towards positive infinity, they might both be going to negative infinity, doesn't matter. But what happens in this case, what we call this is your limit of going toward when x is approaching that specific number, the asymptote, is unbounded. So that means it just keeps going. It just keeps going. Same thing from when it's approaching the right side. It just keeps going. So when this happens, the limit just does not exist because it's just boundless. There's no limit. It just keeps going. The last type of discontinuity I would like to talk about is jump discontinuity. Personally, my favorite one. I don't know why, I just like it. This is very easy to identify it. You know, you see this function I have here. It's going straight, and then boom, it just goes up. So you'll obviously notice there's a break. You'll be able to notice that visually, but algebraically, what happens is the limit of approaching this number, so said number, so this point in this case is 1. So when you're approaching this number, the y value of the left side will not equal to the y value of the right side. So over here, you'll see that when x is approaching 1, so where the break happens, y is approaching negative 1. Now when x is approaching 1 from the right side, y is approaching positive 1. So because these two don't match up, the two-sided limit does not exist. So, but the one-sided ones do. But the two-sided limit does not exist. So you won't be able to prove, you know, like in the continuous function that I talked about, your two-sided limit has to be equal to your function of the set number. But if you don't have a two-sided limit, you won't be able to do that. So, and obviously, you know, it's visually very obvious. It just breaks, and you have to jump. You have to lift your pencil to do this. Okay, thank you for listening. This video is a little long. Well, bear with me, please. Thank you.